Today we'll be discussing the sequence impulse process or SIP and its significant impact on modern blast furnace operation. Coming to our this slide, SIP is as it is already mentioned, SIP is a new blast furnace technology that was first brought into full operation at the end of 2020 in blast furnace number 1 at ThyssenKrupp Steel, Europe, Germany. And following its successful implementation, SIP is now fully adopted into their standard operating practices. SIP is a technology available right now that provides an incremental change aligned with the reducing carbon emission. It can be radially incorporated into existing blast furnace plant, making it a practical solution for decarbonization effort. The fundamental idea behind the SIP is to create a supersonic free jet with a unsteady startup range and a leading shock wave. This condition is highly beneficial for blast furnace process because it intensifies the local turbulence within the raceway. Now, this increased turbulence significantly enhances ignition condition for the injected coal. It also has a cleaning effect on rear area of the raceway, which ultimately leads to much improved chemical conversion of injected fuel. The system requires a high pressure oxygen, typically over 20 bar, supplied from the sites network. This oxygen is delivered via ring main to specialized SIP boxes, with one boxes dedicated to each tier of the blast furnace, as it is shown in this slide. As you can see in this image of installation at BF1, the SIP boxes are located on the platform just above the tier level. The primary function of each box is to generate shock wave and deliver a high kinetic energy oxygen pulse through a dedicated SIP lance is inserted into the blowpipe. Now this lance cooling to ensure the system integrity, each lance receive a continuous flow of basic load the oxygen for the cooling. For safety, a nitrogen supply is also available which automatically switches to emergency cooling if the oxygen supply is interrupted. Now, the impact on the raceway is dramatic. This visualization comparison shows the condition in the coke area with and without SIP. The SIP enhanced the raceway is visibly larger and cleaner. Investigation confirmed that the raceway is reproducibly and significantly enlarged. This slide is very clearly showing. So on average from 1.1 to 1.5, so we can see that zero point 0.4 is the increase in raceway length, and these enlarged raceway and cleaner coke bed significantly improve the furnace permeability, and this allow for a smoother gas flow and better gas distribution throughout the material in the lower furnace. So one of the key outcome of SIP is to improve efficiency, which directly contribute to the decarbonization. The enhanced gas utilization known as ETA-CO leads to CO2 emission reduction between 50 and 100 kilogram per ton of hot metal. So gas utilization improves, and if you go diving deeper into efficiency, the gas utilization calculated as ratio of CO2 to total carbon dioxide increased by 0.6% to 1.4%. That is a ratio of CO2 to total carbon dioxide increased by 0.6 to 1.4% during SIP period. This higher efficiency uh, directly reduces the amount of coke and other reducing agents required for the process. These efficiency gains translate into substantial fuel saving, and compared to reference period consumption of 530 kilogram per ton of hot metal, SIP campaign lowered this figure to 498, which looks very challenging. uh, at this figure. So, as this is showing all details, what we have already spoken about. So, this is saving of around 34 kilogram of reductant per ton of hot metal. Now, a major advantage of SIP is to ability to support higher rate of pulverized coal also, or PCI. By increasing PCI rate, for example, 140 to 170 per ton of hot metal, the furnace can reduce its dependence on coke. So, remarkably, during one evaluation period, the coke replacement ratio is, we can say, uh, exceeded 1.0. This means that the amount of coke saved was actually greater than the amount of PCI that was added, demonstrating a highly efficient substitution of fuel sources. So, the improved permeability from the SIP, as we have discussed earlier already, this SIP's pulsing action leads to a smoother gas flow, and uh, uh, gas flow, and reduce pressure fluctuation, and this has a stabilizing effect on entire operation of the blast furnace. This all about this reduction in your this is the operation stability, how the permeability improve, and finally on a great result across the productivity in the hot metal. So, as we have already mentioned, as a direct result of this stability, instances of process disruption such as hanging and channeling decrease significantly during SIP campaign. This leads to more predictable and reliable operation. Uh, SIP also drive the higher productivity. It enables an increased hot metal, not it's a hot blast flow up to 20,000 cubic meter mm, per hour higher, which contribute directly to increase hot metal production. And the benefit of SIP were highlighted during 6 weeks period of usually poor raw material quality. The furnace equipped with the SIP BF1 maintained 100% production level, whereas a comparable furnace without SIP BF2 could not exceed 85% of its capacity. So, we can say all these that during and this is what it shows, that the thermal load and energy efficiency during these, we have got a lower mole temperature, which also getting converted in terms of optimization of fuel rate. So, we can say these are during the SIP, a lot of challenging situation occur, but with the help of SIP, BF1 could able to perform with a higher gas utilization, a stable reductant consumption, and a better process stability. And the comparison of BF1 and BF2 already shows that with the help of SIP, a lot of process stability and handling, even with the inferior raw material, could able to yield a better production.